Welcome to the September webinar. Today we're going to talk about distributed pumping. It's something, it's called an ECM you probably haven't considered. Well, it's one I certainly haven't considered. Distributed pumping, until recently, I had no clue what it's about, and I still don't really understand how it works, and I bet most of you don't either. What I've been told is that you can have paybacks of, I don't know, 4 or 5 years. I hope that's right. And if that's true, then that means a lot of you, consultants and ESCOs, have been totally blowing it, including myself and including my company, Abraxas. We do energy audits and we don't recommend it, and I think maybe we should be. So that's why we're here to learn what have we been missing here. So Mike Madsen is going to tell us all about distributed pumping. If you guys have any questions, be sure to ask them, because I'm sure you're going to have a lot. And try to prove him wrong. He's been in the business a long time, so he'll probably be able to counter every objection we have. That's what I'm hoping. Anyway, go ahead, Mike. Take it away.
Okay, well, thank you very much. That's me on the left, obviously. I'm Mike Madsen. I've been with Grundfos for 38 years. I am the technical sales manager for distributed pumping. And so it is a great energy saving approach, and we'll spend the next 45, 50 minutes talking about that. Please ask questions or maybe save the questions to the end. We will leave 10 minutes or so at the end for questions. Maybe in the chat box or show of hands, how many of you have heard of distributed pumping? It actually has been around a long time. But it's actually just becoming more prevalent as people are trying to get more green and reduce their carbon footprint and save energy. So it is a great energy saving concept.
Not a lot of hands up. I think I saw 2.
Good. So this is good. So maybe it's new for some people, which is okay also. We're going to start kind of an outline. We're going to talk about a couple pumps and pump systems that you can use for saving energy. This is separate from distributed pumping, but these are the pumps that we use in distributed pumping applications. And you should be using them in your designs and in your energy saving projects. Then we'll do a quick review of how we do HVAC systems today, get into distributed pumping. We'll talk a little bit about the controls and how we control the system. We'll talk a little bit about the Museum of Flight as a reference case. And then after the seminar, we'll send you a nice link for a 3-minute video that you can watch on that case story. So we'll start with a couple products that you should be considering. Can anyone tell me, do they recognize this piece of equipment? Any shout outs or type it in the chat bar. So this is actually a chiller. And so in the old days, that's Mr. Carrier there. In the old days, they would stick build chillers, and they would put in all the different pieces, and that's how they did it in the early days. Of course, you would never stick build a chiller today. You would buy a packaged chiller system. You rely on the chiller manufacturer to put the right controls in, to optimize it for energy savings, and to build everything you need in that chiller. You would never stick build it. So the first product that I want to talk about that's getting more prevalence in the HVAC side of things are packaged pumping systems. So anyone that does plumbing on the call is very familiar with packaged systems. That's the way that they do plumbing systems. But on the HVAC side, the market has been sort of slow to adopt this approach, but they're starting to select packaged pumping systems. And there's a lot of energy saving benefits to using packages. And I just put a few different manufacturers up here. This one happens to be mine here, but there's a multitude of manufacturers that are putting together packages. Some very obvious benefits: smaller footprint, single point power connection, single point connection for your supply and return water. But beyond that, there's a lot of energy saving things that we want to talk about. So I like to start with the motor efficiency pyramid. I'm sure everyone is familiar with NEMA premium motors. That is the lowest efficiency motor that can be put on a pump. Above that, we have IE4, and above that, we have IE5, International Electric Code 5. So just by going with the IE5 motors, you can save your clients 7 to 10% on their energy cost. So if you remember nothing else from today's session, many manufacturers are introducing or have these IE5 motors to put on their pumping equipment. Just by going with that IE5 motor, instead of a NEMA premium motor with a VFD, a wall-mounted VFD, you're going to save 7 to 10% on energy cost.
Hey, Mike, are these IE5s, are these EC motors?
They are. They're ECM motors, permanent magnet motors.
Okay.
And for my product, I actually have this motor available through 30 horsepower. So depending on the manufacturer, they have different things available. The story is actually much more interesting than just saving 7 to 10% energy. What we're looking at on this slide is motor efficiency curves. The bottom one is a 10 horsepower NEMA premium, and the top one is a IE5 ECM permanent magnet motor, 10 horsepower. Here's motor speed on the x-axis. Here's efficiency on the y-axis. This is a 4-pole motor, so my max speed is 1850 RPM. So we can see here at full speed, we're saving maybe that 7% energy savings. We're more efficient by 7%. But what happens is the IE5 motor has a more flat efficiency curve. It stays high longer. And we know whether we're doing domestic boosting, a heating water application, a chilled water application, we spend a lot of our time operating at part load. And so at part load conditions, the energy savings are even greater with the IE5 motor. So we spend a lot of time operating down here, and so we're actually able to generate more than 7 to 10% energy savings. So it's a quick and super easy approach to reduce your power consumption in your designs. Something else we want to do, and for the engineers on the call, I want to encourage you to start changing the way that you write your schedules. Most of the schedules I see today are still coming out with one flow on one head and one efficiency that is at max design condition. What we're looking at on the screen right now is the AHRI chilled water load profile. And what that tells us is we spend very little time operating at full load, and we spend most of our time operating at half load and below. So what we want to do is we want to start selecting our equipment to a load profile. And that's very easy to do. Most of our softwares include an option where we can actually select equipment based on a load profile instead of picking something that's very efficient at this full load condition, but then we spend only 3% of the season operating there. So for the engineers on the call, we would actually start to schedule part load efficiencies for pumping equipment like you do for chillers. And you're going to get better, more efficient selections that way.
And Mike, I just want to make sure I got this. So when we see a pump that's maybe like 87% efficient, that means that's when it's at 100% system flow, right? That's
correct.
87. So really, it's a lot less most of the time.
It can be. So it depends. You want to pick. So an old trick before our software was smart enough to do this selection, we would say in a variable load application, you pick your pump to the right of best efficiency point. So that way, as you slow the pump down, you cross back through best efficiency point and stay on the high part of the efficiency curve.
Okay.
Whereas if you just picked a pump to be very efficient at this full load condition, it may only go downhill from there. It just depends on the selection.
Okay.
Great question. So something else we can do with the packages, this is a curve that shows a big pump, or a package that in this case has 3 pumps. The other thing we can do is when you have a package is you can run a smaller pump to handle your part load conditions. And so we can see the big pump is very efficient. It's 78% efficient at design flow, but we know that we don't operate very often at that design flow. We spend a lot of time down here under part load conditions. And even though I have 3 smaller pumps that are a little less efficient, 72% in this case, when we are operating down here at these lower flows, which happens a lot, we're going to save additional energy. So that's another benefit of having a package, so that we can put multiple pumps and only operate what's needed instead of running one big pump as an example. So the other thing that us manufacturers can do is we can do something called efficiency-based pump sequencing. And it's a simple term. You can either program your controller, or you can have the controller pre-programmed where you load a pump curve in and you load an efficiency curve in. And all efficiency-based pump sequencing means is this is pump 1, this is the efficiency of pump 1, this is pump 1 plus pump 2, this is the efficiency of 1 and 2. And you can see right here where pump 1's efficiency drops below what the 2 pump efficiency would be. And you can see right here where the efficiency of 2 pumps drops below what the efficiency of 3 would be. We can automatically tell the pump, don't operate there. Turn on the next pump. And we can optimize the efficiency over that full operating range. In the old days, I knew a lot of controls contractors and engineers that would write these control sequences. And that's still possible. You know, you can refer to an ASHRAE article and you can optimize the sequences, or you can allow one of us manufacturers to go ahead and optimize it in our pump package, so it's already done. Obviously, there's a lot of energy savings that can be obtained with that efficiency-based pump sequencing. So we're going to reduce our overall energy consumption. We're going to rack up significant energy savings, lower our total operating cost. Sort of a side benefit is as we're running the pumps at slower speed, there's less wear and tear on the equipment also. So running 2 pumps at a slower speed is going to cause less wear and tear on that equipment than running a pump at, let's say, full speed. So a lot of benefits to doing efficiency-based pump sequencing. I did mention, you know, you're also welcome, and I would encourage you, if you're not using a package, you can refer to this ASHRAE article, and it will tell you an approach to do your own efficiency-based pump sequencing. So it is possible to do on your own. I would just encourage you to take a look at several of the manufacturers out there that offer pre-packaged solutions that do this automatically. So that's a little bit on the pump packages. I'll take a short pause. Are there any questions on anything I covered on the packages before I get into another pump product?
I'm going to ask you one, and I'm going to, yeah, there's a few comments in here, so and I'll ask them too. My question is, suppose you're an energy engineer and you're going to recommend, well, they've got, you know, a primary, I don't know, let's say they have a primary secondary system. The secondary system is, for some reason, it's constant volume pumping. You're going to recommend putting a variable frequency drive on that pump, on the chill water pump, and you know, and maybe it's just a standard motor, and maybe we should replace the motor as well so it doesn't burn out. I mean, that's one question. So question number one is, do you recommend that we replace the motors? Because I've heard different people say different things. One, you need inverter duty motors, and some people say no, you can just run the standard as long as the wire's not, you know, the distance between the drive and the motor is not too long, etc. But that was the first little question. But the main question was, if we were going to suggest that, putting in a VFD to control the secondary chill water pump, would you say, no, don't just buy a new motor, get a package instead? Is that what you're saying would be even more efficient?
If I would say if your pumping equipment is at end of life, yes, I would switch to a package. If you just have a motor failure, they're probably going to be more cost effective to put a new motor on. But
Okay,
if your pumps are 20 years old, 15 years old, I would look at replacing the whole pump package.
okay, thank you. That's perfect.
The first question. So if the motor's 30 years old, it may not have been built with inverter rated wire. Every motor today, so whether it's Baldor or US Motor, any of these motor manufacturers, the motors are built with inverter rated wire. So they can all run on a VFD. Inverter duty motors are a little different. So usually you don't need a true inverter duty motor. An inverter duty motor is capable of bigger turn down ratios. So they can do a 10-to-1 turn down ratio, and they have an externally powered fan to cool the motor when you're running at very, very, very low RPMs. Usually not required in our world. Usually the conventional motor with inverter ready wire is suitable. So most of the time you can put a drive on an existing pump.
Okay, that's what I thought. Okay, so here's a question. In Oregon, our code uses pump efficiency index 0.95 or 1 instead of pump efficiency. Is that efficiency metric common elsewhere, or is that just an Oregon thing?
No, it is. That's a national. So that's also a Department of Energy requirement that every manufacturer uses a PEI, a pump efficiency index. And so we all rate our pump. So it gives you a good benchmark. So you can compare brand A against brand B with this PEI value. The PEI value is set at specific flows that may not match a true load profile, but it does give you a good starting point, a good benchmark to compare two products against each other. Good question.
That's all I got for questions. Time to move on.
So here, what I'm showing are ECM circulator pumps, a variety of manufacturers. Mine happens to be the one in the upper right-hand corner. When we get into distributed pumping, sort of the thing we're doing is we're replacing the control valves on the air handler pumps that require a big pressure drop, and we're replacing those with smart pumps. And so we're going to get better flow control with these pumps, and there's some advantages to the pump. So I'll go through some of the advantages first, and then we'll get into the distributed pumping concept. So first advantage, all of these are ECM circulators, permanent magnet circulators. On the left with a conventional induction motor, we're using the electric magnetic field that's created with the alternating power to induce a magnet in the rotor. And that process is not very efficient. So inducing a magnet in the rotor is not as efficient as it could be. By having a permanently magnetized rotor, that's one of the things that makes these ECM motors much more efficient. Of course, in the old days, VFDs were not cost effective. So we saw a lot of systems like this on the left, where we had fixed speed circulators. We had either some heating loads or cooling loads. We had some control valves and a bypass at the end of the line. And so when there was no load in the system and these control valves were closed off, we would be bypassing a lot of fluid and wasting a lot of energy. So in the old days, we would just let the pump run up and down the pump curve. But now with these smart circulators, with these ECM circulators, with integrated controls, integrated pressure sensors, we can actually apply a VFD on a lot of these applications and get a lot of energy savings. So in distributed pumping, we'll use two control modes. One of the control modes is called proportional pressure. And that's what we're seeing on the screen here. And we would use this if we're grouping together groups of fan coil units. So usually fan coil units, maybe they're 10 gallon a minute rating, maybe 15, maybe 5. So what we'll do is instead of putting a pump on each fan coil unit, we'll group together 6 or 8 or 10 fan coils and put the pump in proportional pressure mode. So when all the fan coils are pumping at full flow, that's where we'll be at our design flow and our design head. And then as those fan coil valves start to close, the pump's built-in delta P sensor will have us run up and down this control curve, because we know as we drop the flow rate in the piping system, the friction loss and the head pressure drops. So that allows us to run down this control curve and save all this pressure energy that's shown in blue. That's one of the control modes we'll use in distributed pumping. The second control mode would be to maintain constant temperature. So what we're doing with distributed pumping, we're replacing those control valves with a smart pump. We're taking a leaving air temperature sensor from the air handler, and we're sending that directly to the smart pump. So now the smart pump is working like a control valve, and if we need more chilled water through the coil or less chilled water through the coil, it's just going to speed up and slow down based on that leaving air temperature sensor. That does follow a square function, that control curve. So you can see here at max flow, I can't see my screen, it's behind my picture for me. I think from memory, it's about 58 gallons per minute at 23 feet of head. If the flow requirement's only 50, you can see how much our head dropped and how much our power dropped. So unlike a control valve that just continues to waste energy, when we slow these pumps down on the VFD, we're going to come down this power curve here, and we spend a lot of time operating down here. We're using very little power at these lower flow rates. So again, a show of hands, I'll try to look on the right. So I'm sure everyone on the call has heard about low delta T syndrome. I'm seeing a couple hands go up, I think. Very common problem, low delta T syndrome. Part of that is caused by the building not being balanced correctly. And so maybe we're over pumping some zones, under pumping some zones. But part of that is caused by control valves. There's two types of control valves, pressure dependent and pressure independent. On jobs where we have pressure dependent valves, I'll say that's the application on the left here. As the pressure changes in the system, we get more and less flow through that coil. So it's very common for us to be over pumping a coil. And when you're over pumping a coil, you're sending too much chilled water back to the central plant and contributing to that low delta T syndrome. With these smart pumps, now you can tell the pump electronically, hey, I want you to limit your flow. And so what we would do is we would set the coil rating as the flow limit. So if your coil is rated for 50 gallons a minute, you set a flow limit in the pump of 50 gallons a minute, and you never overpump that coil. So by not overpumping that coil, that really helps you get better delta T back to your central plant. And we're actually in the process of working on a tool. So today, I'll jump ahead and give away part of the presentation, but you're going to save at least 54% on your pumping energy when you go with distributed pumping. And in many real world cases, we're seeing 70% savings, 80% savings on pumping energy. And the question is, well, how much do we save on the chiller, which is actually going to be even more than that? And we're in the process right now of working on a tool to estimate the chiller savings also. Now we're going to get into the meat and potatoes. We're actually going to get into the distributed pumping concept. So we'll do a quick review of how systems are done today. A very common one is variable primary. So with variable primary, you've got big primary pumps or a big primary pump skid, high head, so they're high head pumps. Their job is to keep the chiller happy. And the reason they're high head is they need to supply enough head pressure to satisfy the furthest zone in the system or the index zone. We're maintaining some delta P out there. Here I can see I'm actually maintaining a delta P on a zone halfway out in the system. Then we've got these control valves, and they're controlling flow through the coil, and they're also balancing the system. And these control valves waste a tremendous amount of head pressure. In a couple slides, we'll talk about something called valve authority. And we'll see these valves are adding are using at least 50% of the head that these pumps are producing. Of course, if your load is not very big, we have a bypass here. We'll have a flow meter down here that's not shown because we need to keep the chillers happy. So we've got this bypass valve if the load is insufficient, so we can keep the chillers happy. The other one we see out there is called variable primary, variable secondary. Sort of an improvement in my mind because you've got smaller primary pumps. Their only job is to keep the chillers happy, and we've got a decoupler. There's no valve or no check valve in the decoupler, and so the primary pumps keep the chillers happy and keep chilled water available for the secondary pumps to pull from. The secondary pumps are still fairly high head because they need to produce enough head to satisfy that furthest zone again, that index zone, where we're maintaining some delta P. And then we've got these control valves again. I talked about balancing earlier. So one of the things these control valves do, if we didn't make this closest zone the same pressure drop as the furthest zone, water takes a path of least resistance. So if we didn't balance this zone, we would get a lot more flow through this first zone and very little through the last zone. So these valves have a couple functions. They're doing limiting the flow, they're balancing the zones, and they're doing flow control through the air handlers, but at a pretty significant price, pretty high pressure drops through these valves. Okay, so let's start to look at another example of a conventional system on the left and a distributed pumping on the right. So here I've got a variable primary system on the left. Here's my primary pump, my chiller, my bypass with the motorized control valve, 3 air handler units, and 3 motorized control valves. So often when you guys are going in to evaluate these buildings and they're saying, hey, we want you to propose some energy saving options for our building. The current system's out of balance. I've got some zones that are too hot, some that are too cold. What can you recommend for us where we can save energy and get better comfort in the space? And that's where you recommend distributed pumping. So we still have a primary pump. We've got our chiller. Like primary secondary, we have a decoupler. We have 3 air handlers, but now instead of these control valves that waste a lot of head pressure, we have one of the smart pumps and a check valve. And the reason for the check valve, if this middle air handler is not running, we don't want to short circuit any chilled water through the air handler. You see all the smiley faces. This is a self-balancing system. So if you're a balancing contractor on the call, your balancing job is going to be a lot simpler. If you're doing a new installation, the balancing cost is going to be a lot lower because it's self-balancing. So one way to think about that is we'll size these pumps just like we do most pumps for when all the system is running and all the air handlers are requiring flow. But if this middle air handler and the top air handler are not running, this pump only needs to supply enough water, chilled water, to pull from the decoupler and push through its coil. When this air handler comes on, this pump will speed up a little bit with its built-in VFD and just produce flow to pull from the decoupler and push through its coil. So it's always self-balancing. So sort of the latest and greatest with valve technology, which we're saying we should go away from these valves, is pressure independent control valves. It's the latest and greatest valve out there. Basically what a PIC-V does is it combines all the functions of the other valves into one valve. So it's doing pressure control, it's doing flow limiting, and it's also doing flow control through the air handler unit. So whether you're using pressure dependent or pressure independent, we're going to have all these functions. The pressure independent is just a way to do it all with one valve. So when you look at a linear version of a zone, you've got your balancing valve portion, you've got your control valve portion, you've got your air handler unit, and you've got your isolation valve. And then you'll see the big pressure drop here. between from the balancing valve and the control valve. This big pressure drop is what we want to eliminate. And we need this pressure drop to get what they call good valve authority. And so what is valve authority? So valve authority is how much control that valve is able to exert on the flow. And so if you have very low valve authority, you're not getting any control. So you'll have low valve authority if you have an oversized valve. So an oversized valve isn't going to give you any control. It's going to basically be an on-off valve. The opposite side of the spectrum is if you have a very high valve authority, you're going to get perfect flow control, but it's going to come at a huge cost. You're going to have a big pressure drop to get that flow control. So what's the cost of valve authority? What's the cost of that control? And ASHRAE recommends that you use a valve authority of 50 to 70%. So here I'm showing a conventional variable primary system again, primary pump, chiller, bypass, air handler units, 3 motorized control valves. So a 50% valve authority means that the pressure drop through this top valve here by that top air handler is equal to all the other pressure drop in that zone. So all my piping friction, my pressure drop through my coil, all my fittings, all my return piping, if the pressure drop of the valve is equal to all that other piping loss, that's a 50% valve authority. Now, something to keep in mind, that's 50% of the head with this valve in its fully open position. Now, we already know we spend very little time with the valve fully open. We spend a lot of time with the valve under part load conditions. So these control valves are making up more than 50% of the total head in your system. So you can start to see if we're going to eliminate that head where we can pick up these big energy savings. So here we're seeing again, here's that primary pump skid we talked about. Here's the chillers. Here's the decoupler. And so again, the primary pump skid has 2 jobs. The first job is keep your chillers happy, and the second job is to keep chilled water available for the secondary pumps to pull from. Now with distributed pumping, we don't have a big secondary pump skid right here. Instead, we've distributed those pumps to the loads. So you can see I've got a smart pump on the air handler unit here. I've got a smart pump on this air handler unit. Here I have 1 pump managing 3 fan coil units. And like we mentioned earlier, if we're doing a group of fan coil units, the control mode would be proportional pressure on that pump. And on these pumps here on the air handlers, we're going to be controlling to leaving air temperature. So with distributed pumping, energy conservation, how you can save your clients energy, we're going to save at least 54% on pumping energy. I sometimes have the electrical guys sitting in on a lunch and learn, and when I say that you're going to be able to reduce, we had an example, it was a 100 horsepower variable primary system. And I said, well, you're going to have less than 50 horsepower of pumps with distributed pumping. He said, my service requirements are going to go down. So on a new building, that's a good cost savings. So you've got your pump energy savings. We talked quite a bit about the self-balancing nature. So you're going to save time and money on balancing. And then we talked about using the flow limit to give us better delta T control back to the chillers. So like we mentioned, we're going to take that leaving air temperature sensor that's in that air handler already, and we're going to send that 4 to 20 milliamp signal back to the smart pump, and we're going to replace those valves, and we're going to control the flow through the air handler with the pump. I already talked about flow limit. I will set that up in the pumps so that we don't overpump the coil. And then the decoupler is pretty interesting. So this also helps with our delta T control. And I'll talk through how the decoupler works. So we put 4 temperature sensors, 2 on each side of the decoupler. So here's my chilled water supply. I'm sending 44 °F water out to the system, and I'm sending return delta T 54. When everything's in balance, so when my primary loop and my secondary loop are equal, there's no flow on that decoupler. Let's say you had 10 air handlers running out here in the system and half of them turn off. My primary loop's pumping more than we need. So what's going to happen is we're going to start to move some of that chilled water through the decoupler, and I'm going to see this temperature start to drop on this sensor. That's going to tell the primary pump skid, hey, you need to slow down. The opposite thing happens if we're not pumping enough for the secondary system. So if more air handlers turn on out here, it's going to start pulling some of the return water through the decoupler, and we'll see this temperature sensor start to go up. That tells my primary pumps, hey, you need to pump more, and it's going to speed up and pump more through the for the secondary system. So very simple control strategy, but very effective with these 4 temperature sensors. So I always know we're getting towards the end of the slides when I get to this slide. Everyone's probably a little sleepy. They had some lunch while they were sitting at the desk. What I'm showing on the left, this is a 25-floor building, and it's a building operating at 50% of max flow. We know that we spend most of our time operating at 50% or below. And on the left is a variable primary system, and on the right is distributed pumping. What we've got is a building laying on its side. So this is floor 1 through 25. And so I can see with the variable primary, I'm producing a lot of head on that pump skid, and I'm sending a lot of head pressure out to that 25th floor. These 2 close together dots are the pressure drop through my coil and my air handler. And from here to here are all those control valve losses we talked about. So we've got a lot of control valve losses when we're operating at 50% of max flow. That's what we'll eliminate with distributed pumping. So variable primary, where we're using about 55 kilowatts. If we look over to the distributed pumping approach, the first thing you'll notice is you have a much lower pressure profile. The primary pumps, all they need to do is keep the chillers happy and circulate water to and from the decoupler. Here's a decoupler, or the point of equal pressure. Here's my supply going out to the 25th floor. Here's my smart pump. I almost said my brand there. Here's my smart pump pressurizing, and then through the coil and then the return. So with the distributed pumping approach, you have 16 kilowatts. So you can see the tremendous energy savings opportunity here with distributed pumping. And it's a very, very easy retrofit. I know there's a lot of ESCOs on the call. This is a very easy retrofit to go in and convert a system from conventional control valves to distributed pumping. So a couple slides on the case story. So one of our really nice case stories that we like to talk about a lot is up in Seattle. There's a museum called the Museum of Flight, and they have a lot of wonderful aircraft, priceless artifacts. And they were having a lot of trouble controlling temperature in the space. Some areas were too hot, some areas were too cold. The equipment was aging. It had been put in 1987. So they wanted to do an upgrade. They were putting in some new air handlers, a new chiller, and they heard about distributed pumping, and they said, we'd like to do a distributed pumping approach in this museum. Sort of a medium building, 200,000 square feet. The chiller was a 400-ton chiller. They have 11 air handler units. So we converted the system to distributed pumping. And we have software. So one of the things we can offer you guys, if you're doing a building retrofit, or if you're an engineer that wants to present a traditional variable primary to distributed pumping, we can look at your existing system and we can estimate the energy savings. So we'll do a real nice energy report, and you can use that with your owners to say, hey, here's how much we think you're going to save with distributed pumping. So here at the Museum of Flight, we estimated that they were going to save 58% on their pumping energy. And what they're actually seeing when you get the video link, they're actually achieving 74% savings. We also wanted to be conservative here. We'd hate to tell someone they're going to save 58% energy and then they only save 55 and they're not happy with us. And so we can do a real nice report. I'm going to mention, I think maybe in December, one of my colleagues, Kelly Mosley, is going to be back. He runs our aftermarket group. And so for the ESCOs there, if you're evaluating a building, we have an entire sales team that can help support in the aftermarket. They can come in and they can help you do these energy evaluations. And I focus on distributed pumping, but they can also recommend other energy saving opportunities that we can put together for a building. This is the link I'll send you. It's a real nice 3-minute video. We'll send it after the session today, and it goes through distributed pumping in the Museum of Flight. And with that, that's the end of the presentation from the slide standpoint, but I wanted to leave plenty of time at the end for any questions.
Yeah, I'm going to start with mine first. Mike, I don't even know if folks know who you work for. So can you tell us the name of your company?
Yeah. So
You've done such a great job not being a salesman, which is what I asked. I didn't want you to say, buy my product, we're the best. Everybody else is no good. You were great at that, but at least they should know who you are.
Yeah, thank you. I'm Mike with Grundfos Pumps. And so I've been with Grundfos for 38 years. And I do have, I don't know if it's okay to put this up here, if anyone wants to.
Yes, it is, absolutely.
If anyone wants to get some more information or wants to chat about this in more detail, there is my email. Shoot me an email. If you'd like to have a presentation for anybody, just let me know. So I'm Mike with Grundfos, and I appreciate that. I try to keep it generic.
You're really humble that way. Amazing. Okay, so I got a few questions. One is, do you have, so for people doing energy audits, that's different. I assume you're not going to want to bring, or let's say share your engineers with just an energy auditor, because energy audits, a lot of times people don't do anything with them. An ESCO project's different. If they've already won, a contract with an Air Force base or something like that, then there's probably going to be a project. What can you do, or how can you support energy auditors?
Yeah, so a little bit of both. So we have tools. So like one of the things we have is a tool for domestic boosters. There's a lot of low-hanging fruit out there with inefficient domestic boosters. So we have a tool called a booster check, and this is actually usually done with one of our distributors helping one of the auditors, where we'll fill out the data on the existing system with the booster check, and then we can put together a nice energy savings estimate.
Okay.
And we're also willing. I mean, obviously, we love all the customers. We love the ESCOs because they've already got the contract to save the energy.
Absolutely. Right.
We love the engineers because they're doing new designs. We love the auditors too, because they might do 5 audits, but 1 or 2 of those will turn into a job for us. So we'd like to support all you guys.
For let's say rule of thumb, should we, because sometimes if an auditor want to decide, should I even pursue this or think twice about this, what should I just assume? We take 50% of chill water pumping, and we can probably, we can save 50%. Is that more or less a rule of thumb?
Minimum. You can save 50% on your pumping energy, and really we're seeing 70 and 80%. Okay. What I will say is it makes more sense if your building is, let's say, 70% air handler units. Okay. In Hawaii, they have jobs that are mainly fan coil units, and you can still save energy. You can still save 25% on energy, but the air handler jobs are certainly more interesting when you're saving 50 to 80% on your pumping energy.
Okay, so this looks expensive to me. It does, because let's say you have Well, in your case, the flight building, what was it, 8 air handlers or 6 air handlers?
Yeah.
That's not that expensive, but so you need to put pumps in at all of those air handlers. And then do you need different controls? How do the controls work? I mean, is the BAS controlling these pumps, or how's that working?
So it's a great question. So on a control valve system, we're taking that leaving air temperature sensor, we're sending it back to the BMS system, and then the
Okay.
BMS system is telling the valve what position it wants, what valve position. With us, we're actually doing direct control. So we're taking that leaving air temperature sensor and we're sending it into the smart pump, and
Oh,
we're directly controlling to leaving air temperature leaving air temperature. We can still send data back to the BMS. So another nice thing, we have a single point RS-485 connection. So over a single connection back to the BMS, I can send any of that data that I want back to the BMS.
okay. So
It's
basically,
actually better to have that local control. You know, if on the other way is if you're waiting, there's a delay, right? You're waiting your turn with the packets that they send over the BMS.
well, and also
Direct
people
control.
can override all your strategies on the BMS, and they won't if it's all local. It's just not going to happen.
Yeah.
Oh,
And then of course,
okay.
on the primary side, we've got the 4 temperature sensors doing the control of the primary pump skid. And then again, we can send all that data back to the BMS system.
Okay, but it's all local control. That's great. Okay.
Okay.
All right. So then let's see, we got that.
Oh, wait, cost. That's a big one, right?
Yes.
Cost is a big one.
It's cost
So,
and payback. Yeah.
so the cost is about the same. And you have to think of it this way. So let's say you're looking at replacing a 100 horsepower primary pump package and a bunch of control valves. And instead of 100 horsepower, now we're only going to need 50 horsepower. So your pumps are immediately a lot less.
Right.
So your pumps are less before you even remove the cost of the control valves.
Right.
So you know, the smart pumps are a little more than a conventional pump, but when you look at 50% reduction in power and you don't need control valves, it's really about an equal price. So we're seeing paybacks anywhere from a year and a half to 3-4 years.
Now this is payback, but what about for retrofits?
Yeah. Great question, because retrofit, they make more sense when they're planning something. So we're doing a First National Bank building where they're planning some air handler replacements. Their control valves are at the end of life, and so they need to either replace these control valves. They want a new chiller. So these make the most sense when you've got some other equipment that they're looking at replacing.
Okay.
The payback's a lot longer if you go into a building and they go, hey, everything's working pretty good. We really don't need anything right now. And then you propose, hey, let's change everything. You're not going to have the payback. It might be 7 or 8 years.
That's what I was thinking. So you just can't go in a building and just say, well, we'll do a lighting retrofit and we're going to do distributed pumping, just those two. That's the distributed pumping's not going to be less than 5 years, you're saying, for payback.
Probably 5-ish, or in each case will be different.
Okay.
But when there's other stuff, because these ESCOs and these guys are in there and they're going, hey, look at this. Your valves are at the end of life. You're repairing them every quarter. You're putting in a new chiller. You're looking at new air handlers. Why don't we talk to you about distributed pumping?
Okay, so it's a great add-on when they're replacing a chiller plant or something like that.
Yeah.
Okay, that was really important. Okay, and then does Grundfos offer training or videos or a program for folks that just want to learn more about pumping in general, about the ECM motors and all of that?
We do. So, and I can send this in the same email I send the link to the video. We have something called eCademy. So when you go to grundfos.us, you can find training in there, and then there's little videos on things from how to read a pump curve to distributed pumping for data centers. There's plumbing, HVAC. There's a lot of great training material in there.
Excellent. Okay, I'm going to start reading these questions. I think we might have answered this, but I'm going to read it anyway. How is a primary pump being controlled in a distributed pumping system?
Okay, so we're going to use those 4 temperature sensors on each side of the decoupler. And we're going to use that delta T, or we're going to maintain that delta T across the 4 temperature sensors, and that's how we'll control the primary pump skid. Now we need to remember with a primary secondary system in the decoupler, the primary skid is completely independent from the secondary system. The decoupler makes them into 2 independent systems. And so the primary skid, it's just going to circulate water through the chillers in the primary loop, and then we'll rely on those secondary pumps to do the secondary side. You could, I'm the distributed pumping guy, and I love doing distributed pumping, but you could also go into an existing variable primary system, and let's say their pumps are end of life. Let's say their pumps are 15 years old, and you go, hey, I want to promote a Grundfos packaged pumping system, and we could do a complete variable primary packaged pumping system to just go back in place of what they have today and be more efficient and be a more efficient system.
Okay. Here's a question. Oh, go ahead. Were you still?
No, go ahead. I was just going to say we can do the whole gamut of things. So I'm the distributed pumping guy, but don't let you. Please ask about all your pumps. We can cover all the pumps in the building.
Okay. For a campus with a central plant, can you do distributed pumping only on a few buildings at a time, rather than do you have to do the whole plant?
You really need to do the whole plant. So sometimes if you get into a campus situation, sometimes the primary loop, they have heat exchangers on each building because they don't want the buildings mixing with the primary loop. If you have a heat exchanger, we can do buildings individually, one at a time. But if you don't have heat exchangers, you're going to have something more like what's shown on the screen here. So here would be my primary central plant. We'd put a decoupler at the central plant, and then we're going out with a chilled water supply. And this would be an individual building 2 and individual building 3. We would have a house pump, a decoupler, and then the smart pumps on each air handler unit.
Okay. Can you share the approximate cost of the flight building, the case study? I mean, we don't need to know what they paid, but more or less the cost.
I would need to ask. I'm not sure. I started this position after that job was done already.
Okay. Here's another one. We do a lot of process cooling. Have you seen these successful in industrial facilities where chill water is feeding various cooling needs, not necessarily air handlers?
Yeah, it can work the same. We're just starting to branch out. Our industry team is just starting to promote distributed pumping. There's a lot of interest. I mean, data centers, some people call it industry, some people don't. But yes, we could do this with process cooling as well. Anywhere where they're using these control valves to control the flow, we could look at replacing the control valve with a smart pump.
Okay, so here's one. So you were showing that you said it was like, I don't know, 50 kilowatts to start, and after you were done, it was 15. But was that 50 and 15 kilowatts, was that total pumping of the smaller pumps and the new primary pump, or was that just the primary?
It was total, primary and secondaries.
So these air handlers they're having pumps on them that are what, like fractional horsepower? Is that what you're thinking?
Half horse, third horse, 3/4 horsepower.
Okay, that makes sense. Yes, and that one we got. I am seeing some ones. Do we need so do we still need the BMS to control for the temperature reset? Oh, right, for the
Great question. So yes, so there's so we're doing local control on the smart pumps on the Magna 3s, but then you often want to do temperature reset. So some items in the Magna 3 are rewritable, and so set point is one of those. So you just send the pump a signal from the BMS what you want the new set point to be, and it will automatically switch over to that.
Okay. Here's one. Control valves are typically on the return side of the coil. Would distributed pumps be installed on the supply or return side?
Yeah, it's another great question.
It is a good
You
question.
actually have a good group here. I am pretty excited about this.
I know it's kind of humbling to me because they all know more than I do. Yes.
So in our early days, we showed the pump like this. We showed it on the supply side and the check valve here. So my pump has a built-in temperature sensor. It has built-in flow estimation. And so more often today, we're actually saying, let's put the pump over here on the return side between the air handler and the check valve, because that gives me a real benefit. I know what my supply water temperature is already. My pump
Right.
has a built-in temperature sensor, so I'll know what my return water temperature
Right.
is.
Right.
And I have flow estimation. So now, by putting it on the return, I have BTU information for every air handler. And I can send that back to the BMS system. So great for diagnostic. So when you start seeing some new slides from me, maybe next time you see this or a similar presentation, you'll actually see the pump,
Put it on the other side.
pump
Right.
over here.
Okay, heating hot water typically uses less horsepower than chill water systems. Can distributed pumping be cost effective for hot water systems too?
Yes, yes. So the low-hanging fruit is the chilled water because of the delta T's and the flows. So we're promoting it most in chilled water, but we're doing also heating water. I think our guys are probably from around the country, but on both of the coasts, we're seeing heat pumps being applied more and more as we push towards electrification.
Mhm.
So distributed pumping also makes a lot of sense for heat pump applications for both chilled water and heating water.
Okay. So here's one. How are the pumps ramping up and down? Do they have little variable frequency drives in there?
They do. So you'll probably remember the smart pumps, the little Magna 3 circulators. Those all have integrated VFDs, and most manufacturers have a pressure sensor or temperature sensor in those little circulators. And then you'll remember the IE5 motors that I showed at the beginning of the presentation. Those have an integrated VFD also. So those would be on the primary pump skid, and then we would use our primary pump skid controller to manage those 4 temperature sensors in the delta T. So yeah, all the pumps will have VFDs on them.
All right, so I'm going back to something you already talked about, but we didn't really get it clear. And I want to ask it again, or one of the listeners wants to ask it again. So let's say, I know it depends on the size of the building, how big is the primary pump, how often are they cooling, is it all day or half a day? I got that. You know, I mean, the air handlers, they run all day or whatever. And then also it's the utility rate, which is huge. In California, geez, my rate here in this building is over 50 cents on peak per kilowatt hour.
Yep.
It's crazy. You know, you go to Eastern Washington, it's 3 cents. But okay, but what kind of payback period for retrofits? Let's say you're spending 10 cents per kilowatt hour. Maybe it's a hospital, so they run the air handlers all the time. What kind of payback will we see for a retrofit? Not new design. The stuff's not at the end of the life. It's an ESCO goes in and is looking for projects.
So they're going to promote. So in other words, the hospital they aren't having to service their control valves. They don't need any other equipment. We're just going in and promoting it.
Yeah, it's like 10, 15-year-old equipment or something like that.
Yeah. Well, I think we probably would recommend looking at their pumps to see, 15-year-old pumps, maybe there is better technology out there. So I think we could make a case on a 15-year-old pump system to upgrade the pumps, replace the control valves with something like this. And then we just need to pencil it out. It's probably, I'm just going to guesstimate, it's probably going to be in that 5-year range.
Well, 5 years, good. For 10 cents a kilowatt hour, that's what I said, right?
Yeah,
that's really good.
It just depends on, do they need anything? So if you're going in and everything's working and you go, hey, we want to change all your control valves, we want to change your pumps. Let's say that equipment costs 100 grand just for a number. At 10 cents a kilowatt hour, it's going to take some time to pay that off.
Yes.
So it really is better when there's some other work that we can do in the building.
Okay. Okay. I think I might have made it through them all. Can you, oh, there's some more. Is this also applied to hot water pumping? Yes, we said that to help lower the return water temperature. Oh, for condensing boilers. Yeah, sometimes the return water temperature is too high and the condensing boilers don't condense. I would think that would work for that.
Yeah, absolutely. And another thing we can do is on heating systems, this shows chilled water going out into the system. We can maintain a 10-degree delta T on our primary loop. And in heating, we're probably using a 20-degree delta T on the secondary side. We can set the 20-degree delta T on the secondary side and a 10-degree delta T on the primary side. So very, very flexible.
Yeah, we talked about that. Let's see. Yeah, I'm glad there's a lot of questions here. That means they're listening and you weren't boring. Actually, you talk really well because you're slow and it's perfect. Some people talk so fast you can't pick it up. It's like you give us enough time to think. It's like, okay, yeah, that makes sense. Okay. Perfect.
Hopefully not too slow.
No, absolutely not. No, it's perfectly timed. Okay. Can the BMS change the supply air temperature based on load? Oh, I'm not really sure what that means, but maybe you know.
So I think, I don't know if I understand the question fully, but yeah, so if the BMS system is monitoring all these temperature sensors out in the building and they want to change a set point on an air handler, all they need to do is send a signal to that smart pump to change that set point. So very, very easy to change the temperature set point on the pumps.
Okay. Here's one. How does this work with a centralized chiller that serves maybe 15 or more buildings?
So kind of like the plant or like the district loop we looked at?
Yeah, I think so too, right?
So again, if we have heat exchangers in each building, we could do each building slowly over time. But if we don't have heat exchangers, see, you've got to decouple your primary pumps. If you don't decouple your primary pumps, what happens is, remember, these are high head pumps. These pumps are enough head to serve this furthest zone. So if we converted this close building to distributed pumping and eliminated the control valves, we would push water through the coils if we had high head pumps here still.
This is a primary only. Yeah.
Yeah, with a primary only where you're trying to convert some systems.
Yeah.
What we have seen some campuses do is, we said you can do it a little bit over time. You want to do it as quick as you can, but you're going to leave your control valve in. You're going to put your pumps in, your check valves. You're going to leave your control valve in so that we're not pushing water through an air handler when we don't want to. And then once all your buildings are converted, we'll completely open that control valve or completely remove that control valve. So in that case, you're not going to get all these tremendous energy savings until the job is done, but it is an approach we can use in a campus type application.
Okay, here's another one. So if you have a primary secondary system, you don't need to change the primary pump size. I would assume that stays the same, right?
Yeah, often we don't need to change them. So we had a case story in Singapore where they didn't have enough budget to do the primary side and the secondary side. So we did all the air handlers, we did all the secondary pumps, and we used the VFDs on the primary pump skid to slow that primary pump skid down, because remember, that primary pump skid doesn't need to produce the same, can produce a little less head now. So you could, in most cases, keep that on a primary secondary, keep that primary skid as long as we can add those 4 temperature sensors for control. And then change the primary pump skid later when budget allows for it.
I see. Ideally, though, you would change it, but maybe not the size, but just change the pumps. Yeah, because then it have interior controls, and then they can't override them. What range of horsepowers are available for the smart pumps?
So the IE5 motors, today we go through 30 horsepower.
Yeah, I remember you said that. Yeah, 30.
On the Magna 3 pumps, on my little smart circulators, I can go out to about 260 gallons a minute and 60 feet of head. Then I have other products, like once I need more head or more flow, I have other smart products that I can use, like models that won't mean anything probably to most people, a TPE3 or a CRE3. So when we do a big data center, these air handlers are very, very big. We'll have more, we won't use a little Magna 3 pump. We'll have a much bigger pump for the coil pump.
Okay, I have another question that's a little unrelated, but so I've heard that people, so for a while, I think it was in the 90s or maybe early 2000s, everybody was converting primary only systems to primary secondary systems with a variable flow secondary system. And of course, primary was constant. And then I heard recently, maybe in the last 10 years, they're all doing primary only variable. What do you think of this? I mean, do you think that this primary only system, let's say they're not doing distributed pumping, they're just sticking with these traditional systems, you think a primary only variable flow is better than a primary secondary?
I don't. So it was probably 15 or more years ago that they invented variable primary.
Mm-hmm.
And with variable primary, we've got these very high head pumps, and then we've got the control valve, burning up that extra head pressure that the pump is producing.
Right.
So I think if you weren't doing distributed pumping, I think you're going to get more energy savings from a primary secondary type system, because a primary skid can be smaller, and then the secondary pump is still big and we're still wasting energy. But I think that it's actually going to be a little more cost effective.
I kind of think that too, but I mean, look, I don't know a lot. You know a lot more than I do. Okay, I guessed that one right then. Mike, that was a fantastic presentation. Thanks everyone for coming. Mike, that was a fantastic webinar. And by the way, you are a fantastic presenter. Your pace is perfect, really.
I appreciate that. Thank you very much.
All right, thanks everyone. Come back next month.
Thanks. Bye, everyone.